So in our finite state machine concept lecture, we first talked about the differences between the two types of finite state machines, that is Mealy and Moore finite state machine. We looked at some general block diagrams, and then we started talking about a Moore machine that should vend an item that costs 15 cents, where the vending machine takes in inputs of nickels and dimes. And in order to do this, and this was our first finite state machine design problem, so we made certain assumptions to keep things simple. So for example, the first assumption we made was if the user of this vending machine pays 2 dimes, then the machine is going to keep the change. So it's not going to return back the 5 cents because the item itself costs 15 cents. And there are only 2 inputs, nickels and dimes. We are going to ignore the clock in this example. So if you have any storage elements, that is flip-flops, any type of flip-flops that you might try to use, for all those flip-flops, the master clock is going to be ignored. Instead, we are going to use insertion of a coin as the triggering event to go from one state to the other, or reset as well, right? So even if you press reset on the vending machine, that also counts as an active event which can go from one state to the other. And that leads us into this last assumption, which is must hit reset to restart the machine after vending. So we are looking at this example in terms of the Moore machine, and we will also take a look at this with respect to a Mealy machine. So you can design either a finite state machine depending on the designer's choice. So that's a designer's choice to pick which one he or she wants. The advantage or disadvantage being, if you choose a Moore machine, then the outputs change only when the state changes. With Mealy machine, you can have both types of changes in the output. So outputs could change immediately as soon as the inputs change, or when the state of the flip-flops change as well. Then we went on to looking at this state diagram, which is essentially the first step. So if you start with let's see, is this stuck? Looks like this is stuck. Did it come back up? Not yet. Okay. Hold on, guys. My WebEx seems to be stuck. Okay, maybe now it works. All right, let's see. So back to the same example here, we are looking at the state diagram, which is essentially the first step of our design process. So we take the statements of whatever machine we are trying to design, then by observing the statements very carefully, by evaluating the statements carefully, we come up with a set of assumptions that we would need to make. Some of them are very obvious, for example, the use of reset. Some of them are not so obvious. So when is the transition happening? So depending on the degree of difficulty that you are allowing in your design, you might have to choose those reasonable assumptions. Once you make those assumptions, then you start drawing the state diagram. My first step is usually just drawing the circles out, which means I'm just going to draw 4 circles to indicate the 4 possible states of my state diagram. Now, question is, why do I need 4 states? Because in order to go from 0 cents in the vending machine to 15 cents in the vending machine where I vend an item, I could go from 0 to 5 or to another state, which is 10. Now, the way I reach these states could be different in different ways, but at any moment, my vending machine can have 0 cents, 5 cents, 10 cents, or 15 cents. And if it is at 15 cents, we know that it is going to vend the item. The output is function of the state, which is a property of the Moore machine. As you can see in the square brackets, what appears is the output, as indicated by this green box here. So the green box over here indicates that the output, which in this case is 0, is belonging to the circle, which means it is only dependent on the current state of the machine. That is a property of the Moore machine. Outputs are dependent on the state. Where is the current state indicated? The current state is indicated right in the circle itself, 5 cents. Or in a general case, you might have said S1, state 1 or state 2, right? So in a generic sense, you can use states like this, or for the example that we are looking at over here, these states can be very specific, indicating the amount of money that is currently held by the vending machine. So that's the current state. Next, you have these black arrows between the circles to indicate the state transition. So the circles indicate states, the arrows or the arcs indicate state transitions. And the state transitions happen when there is an input change. So when there is an input that changes or becomes active, that's when the states transition. But the outputs do not change at that moment. The outputs will change only after the transition is complete and the state of the flip-flops is now the next state. So once you go to the next state, that's when your output is going to change. So I hope you guys recognize that difference in when the output changes between a Moore machine and the Mealy machine. All right. Now let's take a look at, so I'm going to erase this quickly, and let's take a look at things that, are should be very simple after you sketch the circles and think about what the arrows should be, right? So how am I going to sketch this? How am I going to put all the details onto this state diagram? 0 cents, 5 cents, 10 cents, 15 cents. I'm going to write those states indicating the money currently in the vending machine right away. Then I'm going to fill out the outputs. Don't lend anything, don't vend anything, don't vend anything, vend an item. 0, 0, 0, 1 for the output. So when the output, whatever variable you associate it with, say Z, if Z is 1, that indicates that the vending machine is vending an item. Otherwise, it is not. After that, I usually start with the reset input. So whenever you reset, you come back to your default initial state. In this case, it is 0 cents because at the beginning, you don't want any money to be present in the vending machine. From any state, you have to talk about all the possible arrows coming out of each circle. So if you are at 0, they are probably 2 very obvious arrows that go out of that state. One is when the input is nickel and when the input is dime. So N and D. So if you get a nickel, you go to the state of 5 cents, and dime, you go to the state of 10 cents. Or you might stay there and you don't get a nickel or a dime, or you keep pressing reset. That's going to qualify as a self loop. So that means that if I don't hit anything, if I don't enter a nickel or a dime, where should I go, right? I will not go anywhere. I'm going to stay there during that time. Okay. So that's when I'm going to stay in the state 0. Next, if I give it a nickel, go to 5, dime, go to 10 cents. Those are the 3 arrows coming out. Nothing, nickel, or dime. Now from 5 cents, the same things can happen again. You can put a nickel into the vending machine, you go to 10 cents. Or you put a dime into the machine, you go directly to the 15 cents. Or you don't give it a nickel nor a dime. Then you stay at 5 cents. So that's the self loop on 5 cents. If you press reset from any of these states, that you go right to 0 cents. So that's captured in that arrow right there. Now, if you move on to the next state, which is 10 cents, output is still 0. You're not vending anything. Neither nickel nor dime. It's a self loop. If you from here, you press a nickel or a dime, either one of them, you go to 15 cents. Remember, we are ignoring we are keeping the change. So from 10 to 15, either one of the inputs active will take us there. And when you reach 15, you will output a 1, which means Z is a 1, which means we are vending an item. And as long as you do not press reset, you will stay there. So the user has to press reset, as stated by the assumption, to go back to the 0 cent state. Now, once the output is given, once the vending machine vends an item, that already has counted as Z equals 1. So it has activated a motion to release that particular item, and it's not going to do that again. It has become, it's not going to keep vending the item. So just note that. All right, so that essentially completes our discussion on Moore machine state diagram. Now from this state diagram, we can go to the symbolic state transition table. From the symbolic state transition table, we can go to the encoded state transition table. From the encoded state transition table, then we go into designing the equations, then to the flip-flop design. So we will take a look at all those steps as we move through these examples. Next, about the state encoding. Now clearly the states that we encoded were only 4 of these, the ones that were of interest: 0, 5, 10, and 15. Now instead, some other designer might come up with a different idea. They might say, instead of choosing 0, 5, 10, and 15, I will choose all the possible states between 0 and 15, which means I'm going to have a state for 0 cents, 1 cent, 2 cent, and so on up to 15 cents, right? But in that case, the designer will only be really using only those 4, because we are allowing only 2 types of inputs, nickels and dimes. So you can go between only these 4. But as a design process, this kind of state diagram should also work, and it does. There are some differences between them though. One key difference is, if I need 4 states, If I have 4 states in my state diagram, that implies that I'm going to need 2 flip-flops to do this. No matter what type of flip-flops those are, JK, D, toggle, whatever flip-flop type they are, we are going to need 2 flip-flops to do this. Because if you have 4 states, then when you move to the state encoding, you can say 0, 0. When say, suppose I say state is S1 and S0, right? And when state is 0, 0, 0, 1, 1, 0, or 1, 1, my D inputs, right? Say D1 and D0. What are those, right? The inputs to the flip-flops, the present state and the next state, those are also going to be 2 of them. So if I have 4 states, I am going to need 2 bits to encode that, which means I'm going to need 2 flip-flops to encode those states. But in the case of 0 cents, 1 cent, 2 cent, all the way to 15, then I'm going to need 4 flip-flops to encode those 16 states, which is not necessary right now, which is, costing more. So that is unnecessary, that is redundant. On top of that, we know that we are never going to use 1 cent, we are never going to use 2 cents. So all those intermediate states are going to count as don't care conditions, which means if I use them as don't cares and combine the don't cares in a K-map to simplify equations, I'm going to have the same problem that I had while designing counters with random power-up states, which are skipped states. In that, if I skip a state, if I randomly power up in that state, I am going to have various possibilities. I may come back into the counting sequence. I may never come back into the counting sequence. That is dependent on how I implement that counter. So the same problem over here. It has forbidden states, right? 0 to 15, all of them adding 1 cent each. That means that there is going to be a possibility of trouble, which means that in a random power up state possibility, the vending machine might behave in a unpredictable manner. Well, you can predict it, but it might give you trouble because we know how to predict that. So if we know how to backtrack our steps and figure out what would happen if the counter, for example, powers up in a skipped state, we know that we can backtrack that by evaluating the don't cares as ones or zeros if you included them in a group or you left them out of the group. So there is a way to predict, however, that is an increase in your trouble. So what is the point of all of this? The point is that try to choose states that are less in number, right? Only as many as you need. The lesser number of states you use, the lesser flip-flops you will use, and the lesser forbidden states or the don't cares you will have. Next, let us try to look at the Mealy state machine here, and we'll try to do the same example with Mealy now. So same vending machine with Mealy. Now if you see, you have your inputs all the way to the left, like the nickel or the dime and the reset, and outputs are all the way to the right. That in our previous example was a mechanism to trigger a motor that releases an item. All the flip-flops are triggered by a master clock signal. Typically edge triggered D flip-flops because the design tends to be very simple in this case. Then you may have a combinational logic before and after the flip-flops. So you may have a combinational logic block, we are calling that F, before the flip-flops, and you may have another combinational logic block over here after the flip-flops. But the difference between a Mealy and the Moore is this particular path. That path wasn't present in Moore. That means the outputs were only dependent on the current state in Moore. Now the outputs are dependent on the current state as well as the inputs themselves. So the current state right here, so if I highlight this current state, I can say the current states can change after active edge of clock. But these inputs can change anytime, because those are in control of the user, right? I can put the nickel and the dime anytime I want. So because of a direct dependence between inputs and outputs through this output combinational logic block G, which has no memory in it, outputs now are dependent on inputs, which can change at any time. So that's the only difference between the Mealy and the Moore. Now same state diagram, but with a Mealy state machine. Let's take a look. We are using the same 4 states: 0 cents, 5 cents, 10 cents, and 15 cents. And right away, you notice that outputs right now are not dependent on the state. If you remember earlier, our outputs were dependent on the states themselves, right? As shown in red. Now they are not. So that was Moore. Now this is Mealy. In Mealy, the outputs are not dependent on the state. They are dependent on the state as well as the input. So you see where the outputs are right now. The outputs are over here, 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 here. So the outputs are now on the arc. They are on the transition that has caused the change. So 0, 0, 0. So all the ones that are highlighted in blue, those are the outputs. Now they are not limited to the state. They are on the arc that caused that transition. So for example, if you are right now in 0 cents, after you press reset, when you enter a nickel, you go to the state of 5 cents, but at that time your output is 0. So when the input is nickel, as you transition from 0 cents to 5 cents, your output is 0. If you enter a dime while you're here, your output is still 0, but you transition to 10 cents. Now when you are at 10 cents and you enter a nickel or a dime, you go to 15 cents when you're and at that time your output becomes a 1. So as you can see here, as soon as as the user entered the nickel or the dime, the output became a 1. It did not wait for the transition to complete and go to 15 cents. All the other aspects of the design are very similar, right? So do not enter nickel or dime. You have a self loop. Reset, you go back to 0 cents. And if you are in 15 cents and you don't press reset, you stay in 15 cents. So that's essentially the Mealy machine alternative of the same vending machine finite state machine. So if you look at both of them side by side, things might look very, very simple in terms of number of states, the arrows, the inputs that are causing those transitions. A lot of things look very similar in terms of Moore and Mealy design. There are some obvious differences. For example, the outputs are not there, and the outputs instead are over here, and so on. So the outputs are now a function of the arc, not the circle. So, but apart from that, there is no clear difference for this particular finite state machine. But if you take a look at more examples, you will realize that a Mealy machine can be simplified a bit further, because we are getting the advantage of output being dependent on the input. So because of that aspect of this machine, it is possible for a particular problem, Moore machine might take more states, might need more states than the Mealy machine. And such an example we are going to see right away. This is our second finite state machine design example. Here we are trying to design a machine that asserts its output. That means it is going to make the output active when the input has 2 or more consecutive ones. So the input is a bit stream, a continuous incoming zeros and ones, arbitrary, right? So there are zeros and ones coming in arbitrarily, and when there are 2 consecutive ones on that bit stream, on that input, we are going to make the output a 1, 2 or more consecutive ones. So if you start off with, we are going to do this with both Moore and Mealy. So first we look at the Moore design. In Moore machine, we have state 0, 1, and 2. And those states we are essentially picking because 0, that indicates that the last input was 0. 1 indicates that the machine got 0, 1. The last 2 inputs were 0, 1. And number 2 is, state 2 is, last 2 inputs were 1, 1. Now, for a moment, just think about what are we missing here? Why are we, we looked at 0, we looked at 0, 1, we looked at 1, 1. Why did we not include last state of 1, 0? Why is this not there? So why are we not interested in making 1, 0 a state? Let us have a discussion on that. So if you think about 2 consecutive ones, right? We are after 2 consecutive ones. So the moment you have 2 consecutive ones, that's when you want your output to go to 1. So let's just come up with an arbitrary bit sequence and try to answer the question that I asked earlier. Right away, you might get a 0, right? To begin with, you might get a 0. And you might want that to be a particular state. Last input was 0. And then, if your new input is 1, your next input is 1, you are moving in the direction of 2 consecutive ones, which means you might want to keep track of that. Hence, we made that also another state 1, right? We said S0 was 0. Actually, you can say this. S0 is got 0. S1 is got 0 1, and S2 was got 1 1, right? That's what we declared in the previous diagram here. Got 0, got 0 1, got 1 1. And I'm trying to discuss why we chose those specific states there. To begin with, we might get a 0 or we might get a 1, right? Or let us have a line here to indicate that there could be another possibility. We could start off with a 1, right? If we start off with a 1, do I need to store that? Last two inputs are 0 1, right? If I reset it, if I make sure that I always reset the machine and it always starts with 0, then my first input is always going to be, in that case, after a 0, right? So that's why I don't have a state which is a 1. I always start with a 0. So I start with a 0 here. If I have another 0, for example, the second bit is also 0, then I don't even need to keep track of this. I can make this my new state, 0, right? That's why I only have S0 to cover both those cases. Got 0. The last input is what I care about. If it is 0, and if it continues to be 0, I don't need to hold on to the previous bit. My new input is 1. That means that I'm trying to move towards the 2 consecutive 1 state. So I'm going to say, yes, I need that 1. So I have a state which is got 0 1. After that, right, now this is where I was going with this. After 0 1, if I got 0, do I need to have another state which is got 0 1 0? No, I don't. I can just use got 0 instead, right? Because I'm not moving in the 2 consecutive 1 state now, the direction in which I want to make the output 1. I'm moving away from that. So in that case, I don't need to hold on to that information of 1 0. I can just make that got 0. The last input is 0. That same state. But if I have 1 here, then my last two inputs are 0 1. Then I move to that, and I have another 1 here. Then I go to got 1 1, and I make the output 1. And if I continue to have 1s here, I will stay in S2 and keep making the output 1. So I hope that discussion was helpful in clarifying why did we not pick got 1 as a state. The reason is we always reset. Why did we not pick got 1 0 as a state? The reason is if you got 1 0, that is the same as saying got 0. I don't need 1 0 because I'm moving away from my 2 consecutive 1s detection. All right, let's come back to this and take a look at how are the transitions going to work. How many states are there? 3 states. So it looks like I'm going to need 2 flip-flops to do this. Where are the input? Where are the states? States are 0, 1, and 2. You might even call them, you might just change this to 0, got 0, got 0, 1, got 1, 1. You can write either one of them. Where are the outputs? Outputs are inside the circles. They are dependent on the state themselves. If you are here, which means you got 0, don't make the output 1. Make it 0. This is got 0 1. Keep the output at 0. This is 1 1. You got 2 consecutive 1s. So make the output 1 there. So that's how inputs and outputs are working for the states. Now let's talk about the transitions, the arrows. If you are here, you know what? Let me just draw this as well. This is also important. So reset, you come to 0, right? You got nothing. if you continue to have zeros there, you stay at that state, right? Self loop. If you keep getting zeros on the input, you stay in that state. But if you get a 1, you move to got 0 1 because that's what you are. You were at 0, you got a 1, you move to the got 0 1 state. So 2 arrows pointing out of each circle. 1 for 0, 1 for 1. The new input being 0 or 1. Now if you are here, state 1, which is got 0 1, the output is 0, but from here you might get a new 0 or you might get a new 1. If you get a new 0, like I said, 1 0 is actually got 0. So you go back to that original, the previous state where your output is 0. But if you get a 1, then you move down to state 2, which is got 1 1, and your output becomes a 1. And from here, if you keep getting more and more 1s, because the problem has 2 or more consecutive 1s. So if you get 3 consecutive 1s, 4 consecutive 1s, and so on, you will essentially be in that particular self loop, keeping the output at 1. But if you get a 0, you go back to got 0 state, and your output becomes a 0. So that is a Moore machine of 2 or more consecutive 1s detector. So it is trying to detect a bit pattern in the input sequence. Questions about this state diagram of Moore machine? Okay. Now let's try to do the same thing with Mealy. Same, it's trying to detect two or more consecutive 1s. In this case, because the inputs and outputs are connected, output is dependent on the input, we can have more possibilities for the arrows themselves. So I only need 2 states for the same problem when done using Mealy machine. State 0 is last input is 0, which means the output is 0 for either input. So if you are here, by the way, it is a little bit confusing as to which one is the input and which one is the output. So I'm just going to clarify this. This one is the input here. And this one is the output. So on the arc, you have input / output. So input that caused that transition, and the output became that. So if you are here 0, if you keep getting the input of 0, your output is 0 and you stay there. If you get a 1 as the input, your output is still 0, but you move to the new state. From state 1, if you get a 1 or keep getting 1s, your output will become 1 and you stay there, self loop. But if you get a 0 from state 1, your output will become a 0 and you go back to state 0. So by simply, the advantage that we have here is that outputs are not dependent on the state. If that was the case, we would need more circles. Now the outputs are dependent on the inputs. So they belong to the arcs. They are written on top of the arcs or the arrows. Because of that, we are able to simplify the design down to 2 states, for which I only need 1 flip-flop. So which is that, right? State 1 is last input was 1 and output will become a 1 for a new input of 1, which is like 2 consecutive 1s there. And output will become a 0 if your new input is a 0. You lost that sequence of 1s. questions about Mealy and more for detecting two or more consecutive ones in an input bit stream. So if you take a look at both these machines side by side, that's what it looks like. 3 states for Moore machine, 2 states for Mealy machine. And the designers prefer that because there is a possibility of doing this in fewer states. And we are able to do that in fewer states only because the outputs are dependent on the inputs as well as the state, but more importantly, the inputs, right? That's the arrows. We can have more arrows, but if you increase the circles, that's what increases the states and hence the flip-flops. Questions here? Okay. Now, let's take a look at reverse engineering the finite state machine. So far what we were doing was going in the design process. So meaning we were designing the finite state machine, not completely, but to the stage, to the state diagram, right? So from the problem, make some assumptions, get to the state diagram, right? So the initial couple of steps we were completing so far. We were not going all the way, but that was the initial few steps of the design process. That was the design of FSM. That's what we were doing so far. Now we are going to do the reverse process, which means the analysis of FSM, right? So what is the design? What is the analysis? So design process starts with the description of the machine, and then it goes through assumptions and it goes through the state diagram. Of course, after that there is a state encoded table, then there is a state transition table, choice of the flip-flop, equations, but eventually it ends with a flip-flop based circuit, right? That's your design process. But the analysis is going to be exactly the opposite. Which means we are going to be given a flip-flop based circuit diagram, and we are going to at least be able to sketch the state diagram. So we are going to go in reverse manner, this to this. And once you are in the state diagram, if you observe things very critically, then you might be able to comment about what that finite state machine is doing. So you may be able to in some cases describe the machine as well. Oh yeah, this guy is a finite state machine that detects two or more consecutive ones. So you might be able to do that by observing the state diagram very critically, but it only happens when you get to the state diagram, and you can get to the state diagram from the flip-flop based circuit by using reverse engineering. And in reverse engineering, the crucial thing is the characteristic equations of the flip-flops. Characteristic equations of flip-flops. That's what is a crucial element in this. Reverse engineering, we give you a circuit, you must tell us what it does, that is, give us the state diagram. So at least give us the state diagram. But in certain cases, you might be able to even comment about what that machine is intended for. In some cases, you might not be able to do that, but in some cases, you might be able to do it. let's start off with a Moore machine. By the way, how do I know that this machine is a Moore machine? Take a glance at the information that is provided on the sheet and please comment about what particular thing that you see on this slide tells you that this is a Moore machine. Alex says there is no feedback from Q. There is no, so there is, so if I go back here, let's see. So there is a feedback in both of them, right? So if you see this, in Mealy, there is a current state going back. That's Mealy. There is a feedback there for Mealy. And for Moore, if I go all the way up now, that was for Moore, there is a feedback. So the feedback from current state is always there. Let's go back to this question now and talk about this. Charles says outputs are coming directly from the flip-flop. Output is dependent only on the state and not the inputs. Perfect. That is the statement right there. Output equals Z. Z is the output of the flip-flop. That's it. Those two together indicate that output is only dependent on the state of the flip-flop. It is not dependent on the input, which in this case is X. Output Z, output is just Z. It is not Z and X complement, right? Like it's not dependent on X. It's just dependent on Z, which is equal to B. B is a state. So by just looking at that, you right away know that it is going to be a Moore machine. All right. Our goal is to reverse engineer this, meaning I'm given a flip-flop. There are two flip-flops here. There are two gates here, logic gates here. There is one input X. Where is X? X is input here, 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 here. Then there is states are A and B. So if the states are A, where is A? A is here. A complement is here. So A complement is there. So to Alex's point, there is feedback here, right? So you see this, there is a connection between this and this. I'm just going to point that out in red. That is a complement. That means those two are connected there, right? So there is a feedback there. We are just not showing it explicitly. We are just using the names to indicate that feedback. All right. So let's try to take a look at how we are going to reverse engineer this. Let us add another page here. Go back and I'm going to quickly pick this up from here and paste it over here. Does anybody remember the characteristic equations for a JK flip-flop? Let me write it over here. So JK flip-flop characteristic equation, right? So let me say JK flip-flop equation. I think it was Q plus equals JQ bar or K bar Q. Can somebody verify this? Let's see. I think this is right, but just to be 100% sure. Where did I put it? Okay, maybe I can take a look at your exams document. I'm just trying to validate the characteristic equation of a JK flip-flop. So if you guys have seen, oh, we have next state tables here. Yeah, that looks right. Sure. Okay, let's assume that it is right. We are going to find out whether it is wrong or not, but let's suppose that is right. So next state is dependent on the previous state as well as the inputs J and K. We are going to need that as well. Now, the first thing that we did here was, because we had two flip-flops, we named them flip-flop A and flip-flop B. And the output of flip-flop A is A and A complement, and flip-flop B is B and B complement, right? So even for the inputs, we might say this is, say, JA and KA and JB and KB, right? Just to distinguish between the J's and the K's. So what equation can I write for A? A is the output of flip-flop A. How can I write that? Well, I'm going to use the characteristic equation just as I did earlier. Q plus equals JQ bar plus K bar Q. So in this case, A plus is going to equal JA JQ bar or K bar Q, right? In this case, our Q is A. Now, what is JA? JA, it looks like, is right now X, the input X. What is KA? It looks like KA is X and B complement because of the AND gate. But we need the pieces to be able to simplify. So if I use what I have written out over here, I can write an equation for A plus as X and A complement, or X and B complement, the entire thing complemented, and A. What is that going to be? X and A complement, or X complement, or B and A, which equals X and A complement, or X complement and A, or AB. So let me box that up here. So that's the first piece. Now let's take a look at the second piece, which is for the flip-flop B. For flip-flop B, we write the same thing again. B plus, oh, come on. B plus equals JB times B complement, or KB times KB complement and B, using the characteristic equation of the JK flip-flop. Over here, Q is B. Next, what is JB? X. What is KB? KB is X exclusive or A complement and B. That's based on the diagram that is shown, exclusive OR gate, right? That means I can simplify a little bit further here. I have X, B complement, X and A, or X complement and A complement and B. Alex says, shouldn't X exclusive or be complemented? Oh yes, you are right. Thank you. So this should be complemented. That means this should be complemented. Well, if this is complemented, that is exclusive NOR, right? So this guy is exclusive NOR. So if I complement that, I get exclusive OR. So I can say this, right? Erase everything. So exclusive OR between X and A. Oh. So I should be able to say X right. So there was an exclusive NOR and I changed it to exclusive OR between X and A complement. Let's keep going here. What do we have? X and B complement, or X and A complement and B, or X complement and A and B. What can I do with this? All right, the first two terms, I think I can pull out a X. I get B complement or A complement and B, or X complement A, B. Continue here. X, and that will be B complement or A complement using Boolean algebra properties. So I get X, B complement, X, A complement, X complement, A, B. I think I can, what can I do here? I can simply pull out a X from the first two. I get A complement or B complement or X complement. Right. All right. So I think I'm happy with this. So this is equation for B plus. So I've got an equation for A plus, I've got an equation for B plus. I also need an equation for Z. Well, Z is pretty simple, right? What is Z? Z is B. So using the circuit given and the characteristic equations of the flip-flops involved, you write next state equations for all the flip-flop outputs as well as the final output of your machine. In this case, Z was the output, right? So we wrote an equation for A plus, we wrote an equation for B plus, and we wrote an equation for Z. in terms of inputs and the current state variables a and b. So x and a and b, that's what we use to write those equations. Wait, but didn't you complement the original? Right, so Alex, you see here x exclusive or with a complement. So I'm going to write my explanation here. Let's see. Maybe I can just write it here. X exclusive or with a complement is actually x exclusive nor with a, right? So it becomes a double complement. All right. Let's see. So we got to that point. Now, once we have those equations, by the way, those are the equations that we derived. Determine the inputs from the combinational logic, derive the next states. So the things that are written on this slide, we just derived that in the previous one. Now from this, we are going to need a table, right? Which is going to be our state encoded state table. So how do I do that? Well, I have the equations, so I should be able to do that. I'm going to probably do that after. Well, let me do it after this current slide. Now for all the state transition tables, it is going to have a particular pattern to it. What is that pattern? The pattern is always going to have present states, inputs, next states, and output. 4 of these always. So actually, let me put it over here. So you should construct the skeleton of your state transition tables in this particular form: present states, input, next states, output. Now for our case, what is our present states? It is going to be A and B. Come on. What is our input? Only one of them, X. What is our next states? A will become A plus and B will become B plus. What is our output? Well, actually, I should say outputs here because there may be many. In our case, it's just one, Z. So form a state transition table that has that particular skeleton: present state, inputs, next state, outputs. And then I just filled it up in blue with our current example: AB for present states, inputs as X, next states of the flip-flops as A plus and B plus, and outputs as Z. So present states obviously can have 4 possibilities, right? 0, 0. Actually, when it is 0, 0, inputs could be a 0 or a 1. So I should say all 8 are existing here. 0, 0, 0. Let's see. 1, 0, 1, 0, 1, 0, 1. 2 zeros, 2 ones, 2 zeros, 2 ones. And 4 zeros and 4 ones. So when the present states are 0, 0, the new input that comes in could be a 0, could be a 1. So I'm capturing all of those possibilities here. So A, B, and X will have 8 possibilities as you are used to filling out the inputs of a truth table. Next, using the equations that we derived, we are going to write A plus and B plus and Z based on that. The easiest is going to be to fill out the outputs for this example, because what Z was equal to B, right? So if Z is equal to B, I can simply pick up B here, copy it, and paste it over here. And I'm done with Z. So that's pretty straightforward. Now, when your present states are 0 and 0, and your input is 0, where do you go? Well, let's try to put that over here. When A is 0, this term goes away, that term goes away, X is 0, that term goes away, so A plus is also 0. So you would fill in 0 here. And then B plus, everything is 0. So if everything is 0 for B plus, this goes to 0, that also goes to 0. So it's 0, 0. So I hope you see that we are using the equations that we derived, obtained by using derived equations. And then you fill out the entire thing. So if you do this right, you should get these values. 1, 1 for the next one, 0, 0 for the next one, 1, 1 for the next one, 1, 0 for the next one, 0, 1, 1, 1, and 1, 0. So I'm not showing you like all the things, but I hope that you are able to use the equations derived earlier and the values of A, B, and X to just plug and chug, right? Like to find A plus and B plus. Z is very simple, it's just B, so we didn't have to work too much for that. Now we have a state encoded table. So how do you go from state encoded table to a state symbolic table? Well, you use symbols instead of states, right? So I'm going to associate states. So for example, when you have 0, 0, I'm going to use that for state 0. And then when you have 0, 1, I'm going to use that for state 1. 0, 1 is here, and that's it. That will be my state 1. Next, state 2, 1, 0. Last one, state 3. So now what you have is a state symbolic table, right? Let's see here. Now using that, I can sketch out the Moore machine. I think we were doing a Moore machine, right? Yes, B is Z. So how can I do this? How many circles do I need based on this? How many circles do I need? How many states do I have? S0, S1, S2, S3. So 4 states, 4 circles. Absolutely right. So let's draw 4 circles here. So state diagram, right? Red, let's see, I have 4 circles. 1, 2, 3, and 4. And let me call this S0 and S1 and S2 and S3. What is the output in those states? Well, S0, Z is 0. S1 output is 1. S2 output is 0. S3 output is 1, right? So 0, 1, 0, 1 in that order. Output 0, 1, 0, 1. Those are your 4 outputs. Next, let us take a look at transitions. If you are in S0, you get a 0, you stay there. You get a 1, you go to state 3. That means if let us do arrows in black. If you are in state 0 and you get a 0, you stay here. Self loop for 0. If you get a 1, you go to state 3. Next, if you are in state 1, you may go to state 0 or state 3 again. So state 1, you may go to state 0 or state 3. Next, if you are in state 2, you may go to 1, 0 was state 2. So self loop or state 1. Self loop for 0 and state 1 for 1. And next, state 3. If you are in state 3, stay there or go to 2. Stay there or go to 2. That's it. That's your state diagram. So we have gone from a given flip-flop based design, the circuit. We have analyzed it and we have ended up with a state diagram. Now in this case, it might be a little bit difficult to figure out what it is doing, but we'll come back to those examples a little bit later. How we can detect what it exactly is doing. Some cases it might be, you may be able to figure that out, but in some other cases you might not be able to figure that out. All right, questions here, how to do the analysis? So I hope you see that the crucial aspect of this, well, I believe there were 2 important things, right? One was to use the characteristic equations of the flip-flops. That was important one. And the Boolean algebra to simplify. But even if you don't simplify, as long as you have the equation, even in the unsimplified form, you should be able to just plug in the bits to get to the state encoded transition table. Once you get to that, then you associate states and then you move on to the state diagram. Also note that this is also important, right? To recognize what is the input, what are the states, what is the output. Why did we call these as the states? Because those were outputs of the flip-flops. Why did we call this the output Z? Because Z was equal to B. Why did we call this the input? The only thing that was left over apart from states and the outputs is the input, that is X. So this is a negative edge triggered flip-flop design that has this particular state diagram. All right. So the steps that I've detailed, we have gone through in detail are essentially written out on these slides, but I don't think there is any point repeating this. Let's keep moving. The following slide lists out the steps of analysis. You guys can read that later on, but given that we have gone through them in detail, I don't see any reason to repeat these. Now, how about this? How do you reverse engineer this? It looks very overwhelming, right? But it turns out if you do things step by step, it is just a matter of time and nothing else. Now, I will point you to this first. So I'm trying to take a look at this particular block first. What do you think that is? The one on the left. What do you think that is? For some reason, it has many inputs, but it only has one output. Which component that did we learn in this class that has many inputs but only one output? Only one output. So we are talking about this guy. No. So here, D0, D1, D2, D3, D4, D5, D6, D7. 8 data inputs. S0, S1, S2. 3 select inputs. Enable. Mux is absolutely right. This is your 8 to 1 mux. Have we seen this before? Have you guys dealt with this before? This exact same one. Have you ever dealt with this before? Actually, it was on the exam. Right there. The second, no, not the second. The first problem on your previous exam was that. And that's the equation that you guys got for the simplest SOP. So the first problem on the previous exam with the select lines as A, B, X and the inputs being either 0 or 1 or Y and your output is F. That was a combinational logic. That was a 8 to 1 mux analysis problem. And many of you have done that right. That is exactly what this is. The 8 to 1 mux over here. It's exactly the same. There's absolutely no difference there. A, B, X, Y, enabled, everything else is the same. So now I hope that you are able to relate to this. JA equals the output of the 8:1 mux, which is AX or BY. AX or BY is the output over here given the inputs and the particular inputs. So if you do the analysis and you know in a very similar manner as you did in your exam, if you do the analysis, then you can write the equation for this line over here, which is essentially the JA input. So this guy connects to that, right? So you can write JA in terms of A, B, X, and Y. Your inputs are X and Y, your states are A and B, and your output is Z. Again, output is Z, that means that this is a Moore machine, right? So you might think that this is a Moore machine for now, because output is only dependent on, oh, hold on, no. This is not a Moore machine. Output is Z, Z depends on A, X, B, Y, which means it depends on the states as well as the input. So this is a Mealy machine, right? This is actually a Mealy machine. The way it is wired, it is actually a Mealy machine. Because output Z depends on A, B, X, and Y. That means it depends on inputs as well as the states. So once you write the equation, so using the mux, you are able to write the equation here, right? And then using some, there are many other gates here. So let me write the gates here. This is a NAND, this is a NAND, which both the inputs are tied together, so it's effectively functioning as NOT here. This is also a NAND, this is also a NAND, also a NAND. These two guys are what? 2 to 4, 2 to 4. So these are decoders. Can somebody tell me the equation here for Q3? The outputs of the decoders are max terms, right? So what would be the max term 3? Max term 3 would be A or B, isn't it? How about here? It would be X or Y. 2 to 4 decoders, the outputs are active low, max terms. The max term 3 when the input is X and Y is X or Y. Max term 3 when the input, hold on, is it? Oh no, I think it's that, right? Yeah, it's A complement or B complement. Max term 3, not it, so I have to complement both of them. Those two are written over here. Decoder output, decoder output. And then the rest of it is combinational. So, well, all of it is combinational except for the JK flip-flops. You are able to use the decoders to write Q3 and Q3 here, equation for that. Then you have a bunch of NAND gates. You have the 8:1 mux. For this is quite simple, right? This one is probably the simplest because you can write the equation here to be A NAND Y. Over here you can write that as B NAND X, and then you can write Z as A Y and B X complement, which is what? A cancels out A and Y, or b and x, right? So that's very straightforward. But if you do all of that, I hope, what are you going to use to write a plus in terms of the input here, ja? Ka, by the way, is coming from this guy. Again, you are going to use characteristic equation for the jk flip-flops, two of them. So if you use all of that and write a plus, b plus, and z equations for those three things, z we have already written here, but a plus and b plus will take you some time. But if you do that, you should end up with these equations for a plus and b plus. And outputs, this is exactly what we just figured out. Using these, you go to the next step, which is present state input, next state output. That is the skeleton. Present state was AB. Your inputs now are XY. So 4 inputs in total. You will have 16 possibilities. You will need to figure out A plus, B plus, and Z using the equations that you derived earlier, which tend to be a time-consuming matter because it's a mux and decoders and a bunch of NAND gates. But I hope there is nothing that is. I hope that exercise is just time-consuming and not something that is difficult. It's just time-consuming exercise. Once you have the equations for A plus, B plus, and Z, you will use these particular input cases to fill out this table. Then you can say this guy is state 0, 0, state 0, 1, state 1, 0, state 1, 1. Fix, then you start drawing the state diagram. Now we can start drawing it, at least a few right away. So for example, when AB is 0, 0 and the input are 0, 0, your next state is 0, 0 as well. And for that, the output is 0, right? So let me say, this is Mealy. So let's see. 0, 0 goes to 0, 0. When the input is 0, 0, output is 0, right? And then when the input is 1, it's the same state. So 0, 0, 0, 1, 1, 0. That means the input possibilities are 0, 0, 0, 1, 1, 0. For all those, output is 0 and it stays there. And when it gets 1, 1, that's when it moves to the next state. And the output is 0 again. And then from 0, 1, you will say, if I get a 0, 0 or a 1, 0, I will go back. When do you go back? When you get 0, 0 or 1, 0. That means X 0. I go back and the inputs are different. So that means I cannot write 1. 0, 0 slash 0, comma, 1, 0 slash 1. So for both those, you go back. For 0, 1, if you get a 0, 1, you go to 1, 0. And the output is 0 there. And then if you get a 1, 1, you go to 1, 0. Output is there. All right. So I've just drawn it up for the first 8 rows, and then of course you can work on finishing. Well, let's just finish it. 0, 0, the new input. If you're starting from 1, 0 here, you get 0, 0, you go here. or you get 1 0. So this I can combine because the output is 0 for both. So I can say x 0 output is 0 and I go there. Then 0 1 output is 1. I go there. If I get a 1 1, I go to 1 1. Output is 1. Now from 1 1, if I get a 0 0, I go back to 1 0. Oh, XX. Oh no, sorry, not XX. 0 0 slash 0 comma everything else. 0 1 slash 1 1 0 slash 1 1 1 slash 1. Everything it goes back to 1 0. All right, so that essentially, that's how you go from the state transition table to state diagram, and that would complete the exercise. One thing to note over here is this. Notice the output Z. Does it match a particular state? Z here is 0. B is also 0. A is also 0, right? And then Z here is 0 0 1 1. What is 0 0 1 1? This is what 0 0. Hold on, no. Hmm? 0 1 0 1. No. Okay, so now I can't do that. All right, so this is that's your state diagram. What is that? I want to say. So output is 0 there, 0 0 1 1 there, 0 1 0 1 there. Okay, so there's nothing we can do there. So that's what we have derived, right? All the arrows with inputs and outputs written on the arc because it was a Mealy machine, and it is a Mealy machine because output is dependent on inputs as well as the states A and B. There are some more examples that are shown on these slides, but I find no use of doing this repeatedly. If you need some practice on this, the slides are there. Refer to those to get some more practice. But I hope that today we have understood the basic skills of doing the reverse engineering. So starting from a circuit diagram, being able to use the equations, logic equations for the combinational gates or the combinational logic components like mux or decoder, and the characteristic equations of the flip-flops. So for example, for JK flip-flop, we used JQ bar plus K bar Q. For a D flip-flop, for example, you would just simply say Q plus equals D, right? So for example, if I was trying to do this, if I was trying to do an equation for this, I would simply say A plus equals DA, right? So whatever the input is, and DA comes from here. So I would say DA equals, this is OR, this is AND, let's see, DA is A or X and B, and that would essentially be A plus. So I think the other elements are pretty straightforward. We have already seen how to do JK. Over here, Z is dependent on A, B, and X, right? if you take a look at this, Z depends on A, B, X, right? So it depends on both the inputs and the states, which means that it is a Mealy machine. But let's try to take a look at this. So going from the flip-flops, going from the circuit to the equations for A plus, B plus, and Z, filling out the state transition table based on those equations, same steps, then going to the state transition table. Going to the state diagram. Now, something that is unique to this example is this. If you observe the output Z, even though logic expression wise, if you look back at Z depends on A, B, and X, right? So if you did the simplest logic expression, or even just some logic expression, it would have A in it, B in it, X in it. And that might indicate that this is a Mealy machine. However, if you very closely look at the state transition table, Z is 00110011, which is exactly the same as B, right? So if logic expression wise it is dependent on A, B, and X, but in reality it is just dependent on B, Z equals B here, right? That's the simplest. So what does that mean? That means that it is wired up as a Mealy machine, but it is behaving like a Moore machine because Z is dependent on B. So it is independent of input X, but it is not wired up as independent of X. So it is still wired up with X coming in, but it doesn't behave that way. It behaves as a Moore. So that is also a possibility. Something that is wired up as a Mealy machine, but it is behaving as a Moore machine. All right. We have a few more minutes left. So let's actually do this exercise. Well, let me poll you guys. Do you guys want to spend time on this particular reverse engineering problem or the other one? Mux based or the simple one? All right, so let's see that it looks like you guys are okay with the designs. So I think this is a good place to stop.